Exam 2. Here are the solutions. We have a screwdriver. We're given a rate of, we're given a torque, okay? We're given a shear modulus and a diameter and a length. And so the question is, what is the angle of twist here in degrees? Okay, so the equation that we're going to be using is that our torque is going to be equal to our torsional spring constant times that angle of rotation. Okay? We're going to need to calculate this spring constant. We're going to use the formula that's there in the book. It's this. Excuse me, that's going to be d to the 4th over 32L. Okay. A times 10 to the 6, let's say pounds per inch squared right here. 0.2 inches to the 4th divided by 32 times 9 inches. Okay. Taking a look at the units, this is going to be pounds here, inches squared, inches to the 4th. There's another inches, so this is going to have units of inches, rather pounds, inches over on this side. Okay, let's plug this back into this equation now. The T we know, that is going to be 15 inch-pounds of torque. This number here, I guess I'll give that. This is going to be 139.63 pound-inch. Okay, or inch-pounds. So we've got 15 inch-pounds is equal to 139.63 inch-pounds. Now times our angle of twist. Now, yes, there's pounds. I haven't indicated whether these are pound mass or pound force. I don't necessarily need to indicate that because we know that a torsion is inch-pound force. Also here, this is force inches. That's going to be the units for this. So we can solve for our angle of twist. .10743. Now this is going to be in radians, so we're going to need to convert this. We know that pi radians is going to be same as 180 degrees. Calculate this. 6.155 degrees. Okay, and that is our angle of twist. Problem number 2. We've got a mass and some springs. First thing we do is we draw a free body diagram. Always, always, always free body diagram. Okay, free body diagram. Here's the mass. Now we've got these springs. Now I'm going to ignore everything that's happening kind of along this surface right here. There's nothing given as far as friction coefficients or damping or anything like that, so we'll just assume that that is frictionless. Sure, there's an mg, but there's also normal force that that pushes back, so all of that balances out. So we can consider this without mass and a normal force, or without the gravitational force and normal force. Let's say that this is going to be our x direction. Okay, so if x is positive, then it's going to be shifted a little bit such that we now have this spring pulling back at Ks. And since the mass has moved to the right, then this spring is also going to be resisting that with a force of Kx. Okay? When we combine this, m I'll do it this way, mx double dot is going to be equal to minus Kx minus Kx. Okay? So when we put it in the standard form, mx double dot plus 0 x dot plus 2kx equals 0. Okay, since we're looking for the natural frequency That's always going to be k over m is our natural frequency. Okay, what that means is not k or m, it means whatever this is over whatever this is. Okay, so our natural frequency here is actually going to be, it's going to be 2 km because there's a 2 right here in front of that. Okay, so that is the answer for number 2, the natural frequency, square root of 2k over the mass m. Problem 3. Which of the graphs most closely represents the step response? Okay, there's a couple of keys right here. The first one is step. Okay, so if you're looking for a step versus an impulse or something like that, you want to look and see where the graph or where the response is settling over time. Okay, so for example, right here, starts at 0 and it settles at 0. So that is not likely going to be a step response. In contrast, starts at 0, but then it settles up here, so that is potentially going to be a step. Same thing here, settles here, back at 0, right? So it's probably not a step. You see how this settles away from 0, so it is potentially. And also this one we see, oscillation is going to be around some middle value, and we see that that is non-zero, so it's likely that that is also going to be a step. So by looking at where it ends up long term is a really good way to determine if it's a step or an impulse or a ramp or some other type of input. Okay, so looking at this equation, in order to identify if it's going to have oscillation or not, if it's going to decay or not, this is information that we can get sure by solving this equation. Oops, didn't mean to cross it out. By solving this equation, but easily we can get just by getting our characteristic equation. Okay, so let's start to do this. We're going to take this and we're going to put it into the Laplace form. We can see that this is going to be 6 s squared x plus 6x equals 3 sf plus 5f. Okay, now our transfer function is going to give us the characteristic equation in the denominator. So if we do that, we would say here x over f. Okay, and so I'm going to take these coefficients, put them on the bottom, leave these coefficients on the top, and then move this f over. Okay, so we 3s plus 5 divided by 6s squared plus 6. Okay, so then our characteristic equation is going to be the denominator here, and we can see very simply this is going to be 6s squared plus 0s plus 6. Okay, that's our characteristic equation, and instantly we can look and see, aha, there's no damping term. Okay, there's no damping term. So by saying there's no damping term, then we know that our answer is going to be this one right here. Okay, there's no damping and it's a step, so that's going to be the one. Okay, if you're not sure, you say, oh, I don't know, let's keep on going. Okay, we would look and see now what are the roots. Okay, what are the roots of this? So we can divide this out. That's going to be 6. Let me change my color. There's going to be 6 times s squared plus 1. Okay, equals to 0. Or in other words, our roots are plus or minus the square root of -1. So these are imaginary roots, and we can look at the table. Imaginary roots gives us oscillation without decay, and again, that's going to be this. All right. So next question, we've got a soapbox racer. Okay. Funny description, right? You run, you fall, and then it just kind of slows to a stop. What I hope you can recognize from this is that this is a situation of drag. Okay, there's no springs, so there's not going to be both the acceleration term and the drag term and the spring constant term. Okay, so very first thing, do a free body diagram. Okay, now we're tempted, I know, and sure, we're welcome to do that, right? We can say mg down as long as we say there's a normal force back up, and sure, those will just cancel on out. We do have here a resistant force of C times V, and that's it. Okay, yes, the forces are imbalanced. That's why there's acceleration, right? Some of the forces is not zero if there's acceleration or deceleration, and that's the situation here. Don't get tricked into putting velocities or momentums or other things like that. This is a free body diagram, okay? And so we can do our equation, right? We'll say mass times v dot is going to be, in this case, all the forces, negative CV, and that's it. Okay, these, the normal force and the gravitational force, they cancel each other out. Okay, so we can take these and put this here in the standard form. M v dot plus CV equals 0. Okay, we can take it one step further. V dot is going to be C over M times V. Okay, oops, plus right here, sorry about that, plus C over M equals V. And so this is a first order equation straight from the table. And so we see that this is in the form of V of T equals, here it is, B over A plus C e to the negative AT. Okay, so we can see that our A is this C over M, which in this case is 1 over 8 or 0.125. Okay, our B is actually 0 because the B is what's over here on the right hand side. Okay, so which is nice, this term cancels out, and what we're looking for is just this coefficient C. Okay, to find that, we would say, well, the velocity at time of 0 is going to be 6 meters per second, and this is going to be in the positive x direction. Okay, and at t equals 0, then this term right here is going to be 1. So then we can see that c is 6, which gives us now a velocity equation. V of t equals 6e to the negative 0.125 t. Okay, that is our velocity equation. What we're asked for, though, is how far does it go? Let's see, how far does it go before it stops? Now, there's two ways to do this, and I'll show you quickly both. Okay, you can say, aha, there's going to be some exponential here, and this is going to decay. How long does it take to decay? Because it never really stops, right? It's always going to keep on going. It never does reach 0. So we could say that tau is just going to be simply 1 over 0.125, or in other words, 8 seconds, which would give us then that 4 tau is going to be 32 seconds. Okay, what we do with this is we say we need to find our position. Okay, so the position that it travels is going to be the integral of the velocity here dt. And this is very, very important that we're going to put in the limits here of integration. Okay, we can go from 0 to 32. As I'll show you, we could also go from 0, maybe I'll do that right here off to the side. 0 to, we'll go to infinity. Watch what happens. Okay. So to take the integral of this term, it's going to be 6 times negative 8 e to the negative 0.125 t. Now this is very important that we evaluate that from 0. Okay, equals 6 times -8 e to the negative 0.125 t. We're going to evaluate this from 0 to infinity. Okay. Now, when we type this in for 32, we end up with negative 0.8791 minus, we also now need to do this, minus a negative, this is now 1, so it's going to be negative 48. Okay. And that's going to give us a distance of, oops, that's going to give us a distance of 47.12 meters. Okay. Interestingly, if we do this now with our limits of integration from 0 to infinity, this actually makes it a little bit easier. Okay. At infinity, this term is 0, to be now 0 minus a negative 48, which gives us 48 meters. If you have at infinity, it's 48. If it's at 4 tau, it's going to be almost there, right? About 90% there. Notice that it's this term is the one that keeps it from being 48, right? And so as the time gets longer and longer and longer, this gets closer and closer to 48. It doesn't go off to infinity because this is stable, and then it stops eventually at 48 meters. Either one of these are the right answer. I actually think I gave a little bit extra credit if you did it this way rather than just finding this 48. Okay, let's take a look at the next question. All right, convert this transfer function into its state variable. First thing is we will turn this back into a differential equation. Okay, y s squared plus 2s plus 1 equals f of s. Okay, so that makes this, let's see, y double dot plus 2y dot plus y equals some f of t. Okay, so I'm going to solve for the highest order. That's this y double dot. Y double dot is going to be equal to minus 2y dot minus y plus this f of t. Okay, so the rules for a state variable equation or state variable form is that you have to have a single derivative on the left and then no derivatives of any kind on the right. Instead of y double dot, we're going to create a new variable. Let's call this y1 dot. Okay, so now we've got this y1 dot, which is going to be the same as y double dot. Okay, that's going to be y double dot. Okay, it might make it a little bit easier if we could define maybe a different one. We would say, for example, y2. Okay, and so we would say that y1, excuse me, so we say y2 dot equals y1. All right. So now let's try to rewrite this equation without there being any dots on the right-hand side, only a single derivative on the left-hand side, okay? And so we would say here, we would say y1 dot equals negative 2, I don't want to have this dot here, so I'm going to use this, y1 minus 2y, oh, excuse me, minus y2 plus f of t. Okay, and then these are our two state equations right there, where we've got single derivative on the left, no derivatives on the right, and that defines this system. Okay, here we go. A mass spring damper. We do not want to treat this that like it is oscillating by its natural frequency, because we do have this damper here. And when there's damping, it's going to oscillate at its damped frequency rather than its natural frequency, okay? And then the formula for that is this. Now the damped natural frequency is the square root of k over m, 1 minus c squared over 4mk, right? So we're given that this frequency is going to be 1.5, so let's set that up, 1.5. Now I'm going to bring this k over m underneath the same square root. So that's now going to be the square root of k over m minus kc squared over 4m squared k. Okay. So we see that these k's will cancel out, and so that simplifies that. Let's go ahead and square this. Okay. So this is now 2.25 equals k over m minus c squared over 4m squared. And so from here, this is really just kind of arbitrary. The one thing I do want to kind of try to do is going to be this term minus some positive number is going to be 2.25. So we'd like to kind of make this be bigger than 2.25 because we aren't going to have those being imaginary. Okay, so let's try to make this, doesn't have to be way bigger. Let's make this, say, 2.5. Right? If we say our mass here is 1 kilogram, then if we have k as 2.5, then that gives us this term of 2.5 over 1, now minus c squared over 4, the mass is 1, so it's going to be 4 times 1, okay? And that's going to be 2.25. So we see, and we can solve this for c, and then we would see that if c were 1, then that would be 2.5 minus 1/4, and yes, that would give us 2.25. And so this system would oscillate at this frequency. Now, there's a whole bunch of different combinations that you can do right here. When I was grading these, I actually developed a little Excel code, and I just type in your numbers to see if it was right or not. And that's the way that I did that. Okay. So the question here now is, what is the forced response? Now, this was the question that I actually simplified for you there in class. I shortened this a little bit, and I said, you know what? Instead of solving the full force response, just give me the characteristic equation. Rather than solving the one that I gave you in class, the simplified version, I'll go ahead and solve this whole thing for you here, just so you can see what I decided to not have you do, once I looked on that in class. Okay. So we'll do it this way. So first thing we would do is we would turn these both into their Laplace forms. Okay. So this first one, this would be Sx equals negative 2x plus 5y. And I need to do better on my 5s. Okay, plus 5y. This one, Sy equals negative 6y minus 4x plus f. And you see I'm dropping off the s's right here. Okay. So we're going to kind of do this like we do simultaneous equations. So I'm going to solve this equation for x. 5 over s plus 2 times y. Okay, and then we're gonna plug that in down here. First of all, we can kind of bring all the y's to this side. So y s plus 6 equals negative 4. Now let's go and substitute this in. 5 over s plus 2 y plus f. Okay, and it's important if we're going to get a characteristic equation, remember the characteristic equation is the denominator of the transfer function. And so I'm not going to do anything with this f. I'm going to get the y over f, and that's going to be my transfer function. Okay, so we're just about there. Let's go ahead and kind of expand this all out. I'm going to multiply everything through by this s plus 2. Okay, so that's going to be y. Now it's going to be s squared plus 6s plus 2s plus 12. Okay, equals negative 20y plus f times s plus 2. Okay, so we can go ahead and move this y over. So now we have y, let's see, this will be s squared plus 8s plus 32, okay, equals f s plus 2. And so our transfer function y over f is going to be simply s plus 2 divided by s squared plus 8s plus 32. Okay, so we can solve these roots if we wanted to find out kind of how they are. They're going to be complex, and that tells us some information about this system, but that's actually not what we're interested in. What I'd asked you to do was to find the characteristic equation, okay, and that was the answer. If you had modified this to make this a minus y, so it'd be minus 2x minus y, then the answer would be s squared plus 8s plus 8. Okay, and that's the characteristic equation. If you wanted to put a 0 out there, that's fine too. I would have accepted full credit. Okay, so many of you had done a whole lot of this first and didn't go back to it after I made the correction. That's fine. And if you had this, I give you full credit for it if you identified it as a characteristic equation. If you did both, I think there was a couple of instances where I saw that some of you had done kind of this one and then halfway the other, and so I actually gave some bonus credit for that, because I know you don't like to have the test questions changed in the middle of the exam. Let me show you why I did change that. Why I did change that question though, from solving the full response. Okay. So this is our y. Let's see. Okay, that is our y over f transfer function. Okay, and if we take this and plug that back into there, then that will give us our x over f transfer function. Okay, x equals 5 over s plus 2 times y. Now we're going to put in all of this. S plus 2 divided by s squared plus 8s plus 32. Okay, this is nice. We can see that these s plus 2's cancel out. And so that gives us x now equals, excuse me, x over f. Let's see, where's my f? Yeah, there should be an f up here. Now my x over f is going to be simply 5 over s squared plus 8s plus 32. Okay, notice you got the same characteristic equation. You were probably expecting that. Now we're going to go in and do something with these input functions f. Okay, so we're saying that our input function here is 3 times this unit step function, which tells us that our f of s is going to be 3 over s. Okay, and so that's what we're going to be adding to these. So we're going to say that x then is going to be now 5 times 3. Now it's going to be s times s squared plus 8s plus 32. Okay, now this takes a little bit of looking, and this is where I wanted to kind of save y'all a little bit of work just because of our limited time. If we go in and look at number 24 on our formula sheet, we're going to see something that has this form. Okay, we're going to look for something that's 1 over s times s plus a squared plus b squared. Okay, if we can put it into this form, then that is going to be number 24. Okay, on our handout, and then we'll know what the time domain solution is going to be for that. Okay, and so this is kind of simple, right? So we say x equals, let's see, that's going to be 15. Here, let me erase this a little bit. Okay, x equals 15 times that. Now this works if we say, let's see, 4. So if we say that A is 4 and B is 4, okay? So what that tells us is that, let's see, I think that's right. So that'd be S, here we go. So it's S squared plus 4S plus 4S plus 16, okay? That would be this term. The thing that's left over is going to be another 16, which is 4 squared. All right. So if we have A equals 4, B equals 4, then that gives us this format right here. And so we can say then that our x of t is going to be 15 times 1 over a squared plus b squared. Again, this is number 24, times 1 minus a over b sine of bt plus cosine bt e to the negative at. Parentheses there, bracket there. Okay. Plugging in our a's and b's, it's not quite as nasty as it looks. This turns into 15 30-seconds. 1 minus sine of 4t plus cosine of 4t, all times e to the negative 4t. Okay, and that is going to be our x of t right there. Okay. Now let's come back and take a look at this y. Let's see, where did I put that? Y. Okay, s plus 2. I'm going to kind of move over here just so I can have some more room. Okay, y over f equals s plus 2 over s squared plus 8s plus 32. Okay, now when we add this f, it gets a little bit interesting, but not too bad. Not too bad. Let's take a look. So y now is going to be equal to 3s plus 2 over s times s squared plus 8s plus 32. Okay, so what we have here is a polynomial on top. We can go ahead and break that apart. That's going to be 3 over s squared plus 8s plus 32. Okay, and that was, I just canceled this s and that s out. Okay, plus 6 now times 1 over s squared. Let me do that. S times s squared plus 8s plus 32. Okay. Now this form we've already seen, right? That's number 24. We can do the same thing. A equals 4, B equals 4. Okay, and we can look at number 10, form number 10. Okay, so if we can get it into that form, then we can simplify this. Watch this. So this is going to be y equals, well, here, I'll just do it like this. We'll just come over here. Okay, so if we say 3 over b times b over s plus a squared plus b squared, okay, then that is going to be form there shown in number 10, okay? And this is like we've done before. That's going to be 6 times 1 over s plus a squared plus b squared. Okay, and so we can convert this back into the regular form. This is going to be, or into the time domain, 3/4 e to the negative 4t sine 4t. Okay, notice that there's going to be some decay and some oscillation, and that's what you get when you have complex roots. And this term is going to be 6 over 32 times 1 minus sine of 4t plus cosine of 4t e to the negative 4t, close brackets, okay? And so y is actually going to be the sum of these, okay? And that doesn't make it too messy because we've got an e to the negative 4t sine 4t, and we've got another one right here. Okay, the sine of 4t and then e to the negative 4t. I'll cut out, oh, excuse me, this is lowercase y. I'll cut out the middle steps for you here and just show you what this looks like to you, what this looks like combined. That's why t. Okay. This is going to be 6 over 32, 1 plus 3 sine 4t minus cosine 4t e to the negative 4t. Okay. And that is going to be the final solution for your y. Here it is for your x. Okay. But since I changed some things, made it a little bit easier, I just had you stop here at the characteristic equation, and that is where you got full credit. Okay, question 8. We're looking for the time constant. Okay, this is pretty straightforward. We need to be careful though, and just not say, oh, it's 1 over 9, or oh, it's 2m over c, or something like that, because there's some special conditions that need to be met. Okay, this equation, this tau equals 2m over c, we actually can't use that because that equation only works if this term is less than or equal to 1, and it's not. Okay, so if you wanted to use this, you would have to prove that you could before you did, or else you'd run into some danger. Okay, so the correct way to do this is you say, haha, this is the characteristic equation. S squared plus 9s plus 14 equals 0. Okay, and so factoring that out, s plus 7 and s plus 2, you can just eyeball it. If you're not sure, you can do the quadratic formula and it will give you these same answers, equals 0. And so then s is going to be negative 7 and negative 2. Those are going to be the roots. Okay, so what we're looking for is the time constant of the system. Right? Now, since there's 2 roots and these are going to be real roots, if we were to look on the chart, we would see that with 2 distinct real roots, then we end up with no decay, and it's going to be an exponential, and no oscillation, and there is going to be decay, and these are going to be some coefficients, and there's going to be an e to the negative 7t. Right, and there's going to be an e to the negative 2t in there somewhere. Okay, and both of these are going to have a certain characterization of their decay. Okay, and so this one, the decay is going to be 1/7, and here the decay is going to be 1 over 2. Okay, in other words, this term is going to decay very fast and very quickly, is not even going to be an issue. Whereas the thing that governs the stability, governs the relaxing of the system, is going to be this term right here, because it has a longer time constant. Okay, the longer time constant matters the most. And so that is our tau for this equation. Okay, the next question here is we're trying to find the transfer function that is equivalent to this block, or to this block diagram. Okay, so As we talked about before, we go kind of forward and then reverse and cancel things out, right? So first we'll just label. And we can do this kind of arbitrary. A, B, C, forward, and then here we've got a backwards 1D. We know that this is C, that this is X, X, all the way around here, okay? So we can, now we're going to go forward, and then we're going to go backward. A, I'll make this capital, is going to be F minus X, okay? B is going to be A minus D. C is going to be B over S. X is going to be C over S. And now backwards, this X is X, nothing happens, and we'll say D right here. I'm going to say D is going to be 3 times C. Okay, and so now we can kind of begin to combine these together. Okay, so A equals F minus X, and now we've got this B. Okay, combine those. So B is equal to F minus X minus D minus 3C. Okay, and then so we'll look now at this term, C, which is B over S, that will make this F over S minus X over S minus 3C over S. Okay, now I'm going to stop here and look because I've got a C on this side, I've got a C on that side, so I'm going to combine these together before I move on. Okay, so I'll multiply everything by S. That will be SC equals F minus X minus 3C. Now I'll group things. C S plus 3 equals F minus X, which means that C is going to be F minus X over S plus 3. Okay, that is my C, and now we come down to our X term, which is C divided by S. X equals C, which is all of this divided by S. So that will be F minus X over S plus 3. Okay, we've got some X's here, so we're going to need to combine all this. I'm going to come up here and make some more room. I'm going to multiply everything by this S here. So this is going to be X. Now we've got S squared plus 3S equals F minus F minus X. Okay, we're going to combine this. Now we've got X S squared plus 3S plus 1 equals F. So then the transfer function F over X over F equals 1 divided by S squared plus 3S plus 1. There we go. That is our transfer function. Okay, for problem number 10, we have a mass and a spring. In the homework, it was a situation kind of the reverse, where we dropped the mass and then it compressed. So here we go, where the mass starts compressed, and then it shoots off. So since there's not going to be any damping, we can use the energy method to do this. And the very first thing we need to do in that case is to define a 0 point. Okay, so it can be whatever you like. I'm going to define mine in my solution as this. So the positive X is up, and that is going to be 0. Okay, which means from a potential energy, gravitational potential energy standpoint, then this is going to begin with actually a negative potential energy, and it's going to have a positive potential energy at the end there for the mass. Okay, so we're going to take everything together, right? The equation that we know, T plus gravitational potential energy, this is kinetic energy, plus this spring potential energy is going to be equal to a constant. Okay, and so we could say this kinetic energy, everything here at state 1, is going to be equal to everything at state 2. gravitational plus spring at state 2. Okay. In both instances, the mass is not moving, so we're going to say that there's not any kinetic energy. And at the end, the spring is fully stretched out, it's fully relaxed, and so there's actually not going to be any spring potential energy here at the end. This gravitational potential energy is going to be mg times whatever the distance is down below this x equals 0, your x equals 0 line. In this case, it's going to be 6 inches or half a foot, 0.5 feet. Okay. Plus now our spring potential energy. The spring normally or unloaded would be 18 inches. Loaded, it's now only 12 inches. So that means there is 6 inches of compression. Okay. That'd be 1/2 K, and then now the 0.5 feet squared. Okay, that is going to be our initial energy. Okay, this left-hand side of the equation, and then at the end, it's simply going to be mg, and then whatever the h is up above this. I'll just call this here. We'll just call this like x star or something like that. Okay, mgx star. Now, I know these things, right? I know the mass. I know what the spring constant is and that sort of thing. So I'm going to take a little bit of a shortcut. So this is a mass, and then this is gravity, 32.2. We know what that is. But I'm going to say that this term, the mass, 38-pound mass times gravity, since we're on Earth, this is 38-pound force. Okay, it's magic, but that's the way that works. 38-pound force times 0.5 feet plus 1/2. We're going to now throw in our K. 490 pounds force per foot times 0.5 feet squared. Okay, equals, again, we're going to say 38-pound force times this x star. Okay. Now here, I know there's not a pound force, but that's what spring constant is. It's a pound, it's a force per distance. Okay, and if you know what the units are for a spring constant, then you won't ever have to wonder about what the units are when you use pounds. Okay, and so the only unknown here we have is x. So we've got this x star, we could say, is 1.1118 feet. And notice that L3 is going to be this 18 inches plus whatever this x star is. So then not L cubed. So then L3 is going to be 1.1118 feet plus 1.5 feet. Okay, which is going to be 2.612 feet. If you want to convert that into inches, that's going to be 31.34 inches. Okay, and that is the answer. Okay, now we're down to our 2 lagniappes. Okay, these kind of dealt with this this question previous. Okay, where we were doing the block diagrams. We've got this characteristic equation from the previous page. That's s squared plus 3s plus 1 equals 0. Okay, and so characteristic roots, we're just going to solve this for the s's, and when we say s equals, we're just going to use the quadratic formula, -3 plus or minus the square root of 3 squared plus 4ac divided by 2. Okay, it tells us that our roots are going to be -0.382 and -2.612. Okay, those are going to be our roots. And since they are real and distinct, real and distinct, then we know that this is going to decay and it's not going to oscillate. Okay. If you wanted to go a little bit further and find our time constants, right? Then I actually gave some extra credit for that. The time constant was 2.618 seconds, right? If you put it down, 4 tau is going to be 10.47 seconds. Okay. So the way I did it, this was +5, and actually, if you gave me the tau, I gave you a +1 and another +1 for that, just because I thought it was cool that you went the extra mile. All right, that's the exam. Thank you very much.